Today we'll be going to cover chunking strategies in production rack systems. On the screen over here, you can see three steps in the whiteboard. In step 1, we'll cover the theory and concepts. In step 2, in the middle, we'll have coding examples which deals with each of the chunking strategy. And on step 3, on the right, we shows a real-world architecture which demonstrate how to apply these chunking strategies in your production rack systems. So first, let's start with step 1. Chunking is the process of splitting your documents into smaller segments for embedding and retrieval. Chunking determines what your vector search can actually find. If you chunk your document incorrectly, your retrieval will fail silently. There is no error message. The system will just return irrelevant context, and then your LLM either hallucinates or gives incomplete answers. The core trade-off you need to understand here is this. Smaller chunks will give you better retrieval precision because each chunk contains focused information. When a user researches for a specific fact, a small chunk containing just that fact will score highly. But smaller chunks, they do lose context. The language model receives isolated fragments without the surrounding information it needs for reasoning. Larger chunks, they do preserve semantic relationships and give you a model more context to work with. However, larger chunks reduce the retrieval precision because relevant information gets diluted by surrounding content. There is no universal answer here. Your chunking strategy should match your content and your query patterns. So let's first walk through the main strategies here. The first strategy is fixed size chunking. This is a baseline approach, and honestly, sometimes this is all you need. You split the documents into uniform segments of predetermined token length. The typical configuration is 512 tokens with 10 to 20% overlap. If your chunk size is 512 tokens, you might have 50 to 100 tokens of overlap between consecutive chunks. So why does overlap matter? Because concepts often span chunk boundaries. Imagine a paragraph where the first half introduces a concept and the second half actually provides the critical example. If your chunk boundary falls right in the middle, neither chunk contains the complete thought. The overlap ensures that at least one chunk captures both pieces together. The limitation of fixed size chunking is that it has zero semantic awareness. A chunk might split a sentence in half. It might separate a question from its answer in FAQ document. It might break apart a logical document right in the middle. For homogeneous content like server logs or transcripts where there is no inherent structure, fixed site chunking will work pretty well. And you should always use it as your baseline to compare against most or more robust and sophisticated approaches. Now let's talk about semantic chunking. This takes a fundamentally different approach. Instead of splitting at arbitrary token boundaries, it uses embeddings to identify natural topic boundaries in your content. Here's how the algorithm works. First, you split your document into sentences. Then you generate an embedding vector for each of the sentence. Then you compute cosine similarity between each pair of adjacent sentences. Whether similarity drops significantly below a threshold or hits a local minimum, you have found a topic boundary. You group all sentences between these boundaries into a single chunk. The key insight here is that consecutive sentences about the same topic will have similar embeddings. They use related vocabulary and discuss related concepts. When the author shifts to a new topic, the embedding similarity drops. This drop signals a natural breakpoint. In my experience, semantic chunking can improve retrieval precision by 15 to 40% on documents with clear topical structure, things like technical documentation, research papers, or structured reports. However, this depends heavily on your content characteristics. If your documents do not have clear topic transitions, you might not see much improvement over fixed site chunking. The trade-off here is computational overhead. You need to generate embeddings during the chunking process itself, not just for the final chunks. For large document collections, this adds meaningful cost and processing time to your ingestion pipeline. Now let's talk about the third strategy, which is the document-aware chunk. This leverages the inherent structure that already exists in the formatted documents. For Markdown files, you chunk based on headers, keeping each section as a coherent unit. For source code, you chunk on functions and classes, preserving the logical units that developers actually think about. For HTML, you respect the tag boundaries. The recursive variant tries the most meaningful separators first. It starts with paragraph breaks, then falls back to sentence boundaries, and only uses fixed size splitting as a last resort. A key practice here is storing metadata with each chunk. You want to preserve the section title, the heading hierarchy, and the source file path. This enables filtered retrieval where users can search within specific sections. It also gives you language model context about where the information came from. One advanced pattern worth understanding is the parent-child chunking. You create small chunks, maybe 256 tokens for precise vector search, But when a small chunk matches, you return the larger per parent chunk and maybe 1024 tokens to the language model. This combines retrieval precision with the context completeness. So now let's talk about the decision framework. Which strategy should you choose? For logs and transcripts with no structure, you should consider using the fixed type chunking. For technical documentation with clear sections, you should use header-based or semantic chunking. And for source code, you should consider using function and class boundaries. For mixed source structure content, you should consider the recursive chunking. The key insight here is that there is no universal answer. You should match your strategy to your content type and measure empirically on your actual data. Now that we have covered the theory and concepts, let's move to step 2, which is the code examples. Now let's talk about the code examples here. So the first example is the fixed size implementation. Here the fixed size chunk function, as you can see here in the code, this takes 3 parameters: your text, the chunk size parameter which defaults to 512 tokens, and the overlap parameter which defaults to 50 tokens. The function encodes your text into tokens and then walks through with the sliding window, creating chunks of specified size. Each iteration moves forward by chunk size minus overlap, so the consecutive chunks share those overlap tokens. This is your baseline implementation that should take about roughly 10 lines of code. Now let's talk about the semantic chunk implementation. So this method takes your text and a similarity threshold parameter which defaults to 0.5. First we tokenize the text into sentences, then we generate embeddings for each sentence using a model like sentence transformers. Then we iterate through adjacent sentence pairs computing the cosine similarity. When similarity drops below threshold, we close the current chunk and start a new one. The output here is a list of chunks where each chunk contains semantically related sentences. The third example here is the Markdown chunk function, which covers the header chunking strategy. This parses the Markdown structure directly. We iterate through the files, and whatever we encounter a header starting with hash symbol, we close the current chunk and start a new one with that header as metadata. Each chunk in the output includes the title, the content, and the full header path for filter retrieval. The fourth example here is the evaluate chunking function. So this is critical because you need to measure whether your chunking strategy actually works. The function takes your chunks, a set of test queries, and ground truth and relevance labels. For each query, it performs a vector search and computes 2 metrics. Recall measures how many of the relevant chunks appear in your top results. MRRR, which stands for mean reciprocal rank, measure how highly your correct chunks are ranked. You should run this evaluation comparing different chunking strategies on your actual data before making a decision. So now that you have seen the theory, concepts, and the code examples as well, now let's move to step 3, which is the real world architecture diagram for a production system. So this is an example architecture diagram for an enterprise documentation search system, which should be ideally be able to support 10,000 engineers searching across 300k documents. Looking at the architecture diagram, you can see document sources on the left feeding into an ingestion pipeline. The key component here is the document router. This router examines each incoming document and sends it to the appropriate chunking strategy based on the file type. Markdown files will go to header chunker, Python, JavaScript, and Go files will go to function chunker, and PDFs will go to the semantic chunker method chunker component. And also the log files, as you see, they will go to the fixed size chunker component, and each chunker component will produce chunks with appropriate metadata, which then flows through the embedding generation into the vector store. On the retrieval side, user queries get embedded, search against the vector store, pass through a re-ranker for improved precision, and then the top results become the context for the language model. Now let's talk about the router pattern in more detail. So the documented router is the key architecture insight here. Rather than using one chunking strategy for everything, we match the strategy to the content type. This routing adds minimal latency but significantly improves the retrieval quality because each document's type gets chunked in a way that preserves the natural structure.